Hello and welcome. Have you ever sat in a math class or maybe you've been watching your kids do their homework and you just find yourself wondering, why are they teaching it this way? It's a really good question. So today, we're going to go on a little journey to find the answer. We're going to trace how a really complex mathematical idea makes its way from the mind of a scholar all the way down into a student's notebook. All right, let's dive in. But first, let's start with a kind of provocative question, just to get us thinking. What if the whole point of math class isn't actually about finding the right answer? What if it's about something deeper, something more fundamental about how we think? Just keep that question in the back of your mind as we go, because we're going to explore the hidden architecture behind modern math education. So our journey starts right at the source. The math that ends up filling our textbooks, it doesn't just appear out of thin air. It has to be very carefully selected, translated, and adapted from this huge, vast world of professional mathematics. And this whole process actually has a name. It's called didactic transposition, a concept from the sociologist Yves Chevallard. Think of it like a three-step translation. First, you've got scholarly knowledge. That's the raw, messy, complex work that mathematicians do. Then, that gets transformed into knowledge to be taught, which is the neat, tidy, official curriculum. And finally, the teacher takes that curriculum and interprets it, creating the knowledge actually taught. The key thing to realize is that at every single step, the original idea gets changed a little. This means the math you learn in school isn't the raw material. It's a very specific, processed version of it. Okay, so we've got a curriculum. But now the question is, how do we make it actually come alive in the classroom? How do you make these abstract ideas feel real and relevant to students? Well, this is where a really powerful philosophy from the Netherlands comes into play. Now this is one of my favorite little details. When we hear realistic mathematics, we immediately think of real-world problems, right? Like calculating a shopping bill. But get this, the name actually comes from the Dutch verb for to imagine. The goal isn't just to connect math to the real world, but to present problems that are, quote, experientially real in the student's mind. So that could be a real-world problem, sure, but it could also be a problem from a fairy tale, or even from the formal world of math itself, as long as the student can truly imagine it. And this whole philosophy is built on 6 core principles. First up is the activity principle. This is the simple but incredibly powerful idea that you don't learn math by just listening, you learn it by doing. Instead of just being handed a formula, students are pushed to be active participants, to develop their own tools and their own insights to solve a problem. Second, we've got the reality principle, which we just touched on. The starting point for learning should always be a problem that feels meaningful and imaginable to the student. This creates a really rich context that they can use to build their understanding from the ground up, instead of just starting with abstract rules. The level principle recognizes that learning isn't just one single jump from not knowing to knowing. Students actually move through different levels. They start with informal, context-based solutions, and then gradually they develop more abstract and formal strategies. Models and diagrams are absolutely crucial here. They act as a bridge between a concrete situation and the abstract math. Next is the intertwinement principle, and this one is so important. Instead of teaching algebra in one box and geometry in a totally separate box, this approach sees them as heavily integrated. Students solve these rich problems where they have to pull ideas from different areas of math, which, let's be honest, is much more like how math is actually used in the real world. Then we have the interactivity principle. This says that learning math isn't a solo sport, it's a social activity. Through things like whole class discussions and group work, students get to share their strategies, they get new ideas, and they reflect on their own thinking to reach a higher level of understanding together. And finally, the guidance principle. This is all about the teacher's role. They aren't just a lecturer standing at the front of the room. They are a proactive guide. They create these scenarios that allow students to go through a process of guided reinvention, where they essentially discover mathematical concepts for themselves. So we've got this rich, interactive classroom, but now let's zoom in even further, right into the mind of an individual student. How do they actually process a math problem? Well, it turns out, to be successful, they have to become fluent in several different languages of math. This slide illustrates the work of cognitive scientist Raymond Duval. He argued that mathematical thinking really involves 2 key processes. The first one is called treatment. That's when you work inside a single language, like using only the rules of algebra to solve an equation. But he said that true, deep understanding comes from conversion. That's the ability to translate an idea from one language to another, from words to a graph, from a graph to an equation, and back again. He called these languages semiotic registers. So for example, here's a problem in the language of words. We've all seen these, right? It's a description, it's a narrative. This is one semiotic register. And here is the exact same problem, but it's been translated or converted into the language of symbols. Being able to make that leap, to see that these two things that look totally different actually represent the exact same mathematical idea, that, Duval argues, is the biggest hurdle, and also the biggest key to learning math. Of course, the person who has to orchestrate this incredibly complex dance of transposition and realism and cognitive conversion is the teacher. So how do they get better at their craft? How do they reflect and improve? The work of Donald Schoen gives us two really powerful concepts here. Reflection on action is what we usually think of. After the lesson's over, the teacher sits down and thinks, okay, what went well? What could I do better next time? But reflection in action, now that's more subtle, and it's way more powerful. It's when a teacher, often because of some surprise in the classroom, reshapes what they're doing while they're doing it. It's literally thinking on your feet. And this kind of reflection isn't just random. A lot of teachers use a systematic process called the action research cycle. You plan a lesson, you act on it, you observe the results, and then you reflect. And those reflections feed directly into the next plan. It becomes this continuous, critically reflective spiral of improvement. Okay, so let's zoom all the way back out. We've gone from scholarly math to the curriculum, into the classroom, inside the student's mind, and into the teacher's own practice. What's the ultimate payoff for all of this? Well, it's to prepare students not for the certainty of the textbook, but for the fundamental uncertainty of the real world. Let's look at a classic experiment from the psychologists Daniel Kahneman and Emis Tversky. In the first scenario, you can have $1,000, for sure. Or you can take a 50-50 gamble for $2,500. What would you do? Now, look at the losing situation. You can lose $1,000, for sure. Or you can take a 50-50 gamble on losing $2,500. Research shows that in the winning situation, most people take the sure thing, option A. But in the losing situation, most people actually take the gamble, option B. So let's look at the pure math here. The expected value of that gamble in the winning situation is $1,250, which is more than the $1,000 sure thing. So the mathematically rational choice is to take the gamble. But that's not what most people do. We are, as they say, risk-averse when it comes to gains. And you guessed it, the reverse is true for losses. The expected value of the gamble is losing $1,250, which is worse than the sure loss of $1,000. And yet, people still take the gamble. We become risk-seeking to avoid a definite loss. What this really shows is that even when we have all the numbers, our decisions are shaped by human psychology. The math doesn't happen in a vacuum. Which brings us right back to our first question. All of these modern approaches to math, from didactic transposition to realistic problems to understanding the different languages of math, they're about so much more than just finding a single right answer. They're about developing a flexible, imaginative, and critical way of thinking. They're about preparing us to navigate a world that is messy and uncertain and full of gambles. So maybe, just maybe, the ultimate goal isn't just teaching students to solve for X, but teaching them how to solve for the unknown.